started on the project. Are there any other questions people have at this point? Hopefully you're having fun being a crypt analyst here. Not pulling your hair out too much. I see a lot of hair in this room, so I think that's a good sign. For the people who are here, at least, I can't talk about the baldness of people not present. Let's see, another quick note is I have office hours right after class today because I was out yesterday. It was my birthday. I turned 49. My wife turned 50 yesterday. We shared the same birthday, and so it seemed like a good reason to skip office hours, so I apologize, but it was a good day. And then on Thursday, I am going to a program committee meeting for the Usenix Annual Technical Conference. This is where all the readers of papers sit in a room and decide which papers to accept and which to reject. So it's being held at VMware Research in Palo Alto, California, and about 50 people from around the world will spend about $1,000 each to go to this meeting. So there'll be about $50,000 spent on planning this conference and picking out sort of the top 40 papers out of the 500 submissions or 400 submissions to sort of pick which ones actually get to be presented at the conference in July. And one thing to note, if any of you write papers, is that the papers that get there's been a bunch of studies that sort of show the bottom third of papers, no matter who is on your program committee agrees they should be rejected. But if you look at the papers that get accepted, if you pick 2 program committees of the same population of researchers, you will get approximately like 60% disagreement in which papers should be accepted. And so there is a huge amount of randomness in academic publishing on whether somebody had a good day, whether somebody really likes your work or doesn't like your work. And so getting a paper rejected, you know, you can take some solace in the fact that it was a pretty random process. Or you can be frustrated and quit academia and go do something useful with your life. Okay, sorry to rant about that. So we're talking about virtualization, and we're going to go into some virtualization-related vulnerabilities. What's interesting is a number of these works I was a participant in, or Tom Ristenpart, who was a professor here for 5-6 years, was a participant in, and a lot of it was done by students here. So the things we're going to talk about are what are called reset vulnerabilities in dealing with randomness in virtual machines. We're going to talk about side channels, which is when information unintentionally leaks out of one program and is visible to another program. And then we'll talk about leaking secrets because people are sloppy. So the key thing to think about is when we're dealing with virtualization as a security topic, there's a lot of it that is the same as normal computing. We still run applications, we still run operating systems. All the vulnerabilities in applications we talked about with buffer overflows, with server-side, with cross-site scripting, all those things still exist in a virtualized setting. And so the thing that security researchers do is figure out what is different. How is a virtual platform, when you're running your operating system in a virtual machine, different than a native hardware platform? And there's a couple of key differences. One is there's things you can do on a virtual machine that are very difficult to do on real hardware. So one thing you'll do that we can do, we'll talk about, is that you can save the entire state of the virtual machine, every byte in memory, the values in registers, you can save it and then reload it later. So this is a lot like hibernation when you close your laptop and it opening up again. The difference is here you can do it multiple times. So you can save a copy of your state of your running operating system. You can restart it later. You can then roll back and restart it a second time, roll back, restart it a third time. You can even move it from one machine, so you restart it on multiple different machines simultaneously. With real hardware, you can't sort of roll back time and reset things necessarily. So this creates new vulnerabilities. Another is the changing of assumptions. So we'll talk about this a little bit. You may have wondered, how does your operating system get random numbers? Right? Processors are fairly predictable. They always compute the same thing when you give them the same sequence of instructions, we hope. So when you need random numbers, where do you get them? And what this means is operating systems have to find things that are random and use that randomness in order to create random numbers. And there's a chance that a virtual machine with virtual hardware might have different amounts of randomness in the virtual hardware than in real hardware. And then finally, another thing in virtual machines is that when you're running your operating system alone, your operating system owns the entire hardware. So there's nothing shared with any other user, which means that whatever you do to that hardware, however you use it, stays within the operating system. In a virtualized platform, you're running 2 operating systems, and so it's possible that what you do with the hardware on one operating system is sort of leaked and is visible to another operating system running, or that one operating system that's running can do things to intentionally disrupt another one by sort of overusing hardware or something like that. So we'll see some examples. So what we're going to start off with is talk about these reset vulnerabilities. And these things come out of a feature called Snapshots. And in Snapshots, Snapshot again is this idea that we can take a running virtual machine or a paused one, and we can save everything, and then we can restart it later. You may have used this in doing project 1 and 2, where you paused your virtual machine to come back to work on it later. So one kind is a volume snapshot or a checkpoint, and this is really just a copy of the disks. This says whatever we had on disk we want to make a copy of, so that if we install new software, you know, whatever we had before is still there. If the software is buggy, we haven't corrupted things, so we can roll back to an older copy of everything on disk. But this means when you have a volume snapshot, every time you start up the virtual machine, you're rebooting the operating system, going through initialization from this copy, this sort of snapshot of what was on disk. And then you sort of execute forward and modify a copy of the disk, but there's still a clean version that you booted from available later. The second thing is what we call a full snapshot, and this contains not just everything on disk, it contains everything in memory. Every byte in DRAM, every byte in your cache, every byte in your processor registers, the configuration of your device drivers, all of that information. And so here, effectively, you're running a virtual machine. At some instruction boundary, the virtual machine monitor or hypervisor will say, we're going to snapshot now, and it saves every single bit of state. And it can do this because it's all in software. Normally, this information is embedded in hardware, and so you actually have to execute on the same hardware to save your state, and so you sort of end up changing the state as you execute. Here, because it's all software, we can save a copy to disk somewhere and boot up later. And then a VM image, which you have used, is really a file that stores a snapshot. Any questions on the terminology and the ideas here? Okay. So we're now going to sort of look at where this breaks things. So what we need to understand is the role of randomness in security. So we have run across randomness in several places. So when we looked at our cryptographic protocols or mechanisms like cipher block chaining and block ciphers, we needed random numbers as an initialization vector to do encryption. We used random numbers in salting when we salt passwords. We used random numbers in TLS. We had these nonces we sent back and forth that are supposed to be random. So many security protocols need a good source of randomness. And the property we want is that it should really be unpredictable. That if somebody knows what number you're going to use, then they can defeat your system. So that is what is important, is making sure your random values are totally unpredictable and not reused. The second place we use randomness is in system security. So we've talked about a bunch of these. For example, the sequence numbers used in TCP/IP. We talked about if these are predictable, somebody can spoof your TCP/IP session and hijack it and send data as if it was you. We also talked about address space layout randomization as a defense against stack smashing because we move things around. Here we need random numbers to sort of randomize where things go. If it's predictable instead of random, then an attacker can sort of predict where things are in memory and launch the same attack. And then stack canaries are another example where we put random numbers on the stack, and then we check them after a function call and see if they've changed. Again, if these aren't random, then an attacker can generate code that can defeat this. So where do we get secure random numbers? So every operating system, usually inside the operating system kernel, has some way of generating relatively high quality random numbers. In Linux or OS 10 from IBM Apple, there is a pseudo device called /dev/random or /dev/urandom, and if you do cat on this, it'll just produce random numbers for you. So this is how you get random numbers in Linux, is you read from /dev/random or /dev/urandom, and it gives you random numbers. So a few quick things to note is that /dev/random is rate limited. It will only give you entropy, random numbers, at the rate at which it can generate random numbers. So the idea is there's some input of randomness that it uses to create random numbers, and then it creates them. If you run out of randomness coming into the OS, it will stop producing random numbers. /dev/urandom will always give you random numbers, even if they're not very random. And the idea is sometimes you want you really want guaranteed high quality randomness. Other times you want pretty good randomness, and you really don't want to block the user waiting 10 seconds for something random to happen. So let's sort of see how this randomness works. So we have this random number generator called an RNG. And then the source of randomness people have settled on is sort of the outside world, which are devices that plug into your system. The thinking here is everything the processor does is pretty deterministic, but that the outside world, when somebody types on their keyboard, when a hard drive generates an interrupt saying there's data available, when a network packet arrives, the timing of those events are pretty random. So what we will do is take these system events from the outside world, take the time of when they happen, treat that time value as something random, and capture that randomness somehow. And then we will use that to produce sort of statistically high quality random numbers. So in Linux, what happens is we have these interrupt events. They go into what's called an interrupt pool. So the kernel has this notion of a pool of entropy, which is just sort of gathering random information and storing those bits of random information into the pool. So for things that are very frequent, suppose you get interrupts every millisecond. So the upper, if you measure the time, the upper digits in milliseconds might be pretty predictable because every millisecond you get something. So it's really the low digits, the low bits of microseconds. How many microseconds between events are random. And so it adds those bits of microseconds into this interrupt pool. For things that are less frequent, like keyboard, there's more randomness of when you type on your keyboard, and so it might use more bits. But essentially what you're doing is analyzing every source of randomness to figure out how much of it is actually random and how much is predictable, and just taking the random part. We then put it into an interrupt pool. We then sort of take that interrupt pool, and there's an input pool of randomness that will pull bits from here when it needs randomness, and it feeds them into a random pool. This is the one that's blocking that I mentioned before, where it waits for new randomness, and the urandom pool. And every time it does this, it applies a cryptographic hash like SHA-256 to sort of further mix things up. And then from this pool in the middle, it will also apply a SHA-256 to sort of create the final output. So the thing to note is the random events come in, they go into an interrupt pool, bits kind of sit there for a while. At some point they move to the input pool where they can sit for a while. And then when we need randomness, they will sort of go into the random or the urandom pool where they will sit for a little while, and then they will be pulled out when somebody reads from /dev/random. So there is a time lag between when the random things happen and when the random numbers are generated. Does it make sense? Yes? So the rand function in C, I believe, doesn't, it depends on implementation. It may not invoke these. This would typically be used in the srand function where you're providing a random seed to start generating numbers. So these are pretty slow. They require a system call. The access to dev random might be slow. So what often happens is when you start your program, you will go to the operating system and say, give me a random seed. And you provide that random seed to the C library or Java library that's generating random numbers. And then you just use that library function for generating random numbers after that. And what that will do is basically do things like multiply your current seed by some large number and then take modulo by some other number that gives you a very random looking sequence. But it's very fast. Or you can repeatedly apply a cryptographic hash over and over and over again to generate new random numbers. But you would typically access these functions. Often programs will only access dev random or dev urandom when the program first starts up. Excellent question. Yes? So dev random, if their random pool is empty, dev random will block. And it will wait until new interrupt events happen and new randomness flows between the interrupt pool to the input pool to the random pool. Dev urandom will never block. So even if it's already used all the randomness, it will keep giving you random numbers. They're not as good, but they're better than nothing. And it's better than having a user mode program try to do this on its own is the idea. So you might have an inkling of how things are going to go south. So there's a couple of things that RNGs can do wrong. Things they can do wrong is have a predictable output where you can guess, perhaps having seen a sequence of random numbers, what the next random number will be. If they have a repeated output. So, for example, if you were generating a secret key for encryption from this randomness and you happen to get the same randomness twice, you might generate the same key twice. And we've seen schemes where this is catastrophic because it lets you sort of reveal all the secret information, like a one-time pad. The other thing that can happen is that if your outputs are from a small range, so they're not actually using the whole 256-bit range that a random number can give you, if they're all sort of 32-bit values. So for example, in WEP, wired equivalent privacy, an early Wi-Fi encryption mechanism, they used an RNG with a 32-bit seed, which meant that it was somewhat predictable because you could sort of guess one of those seed values. Another thing a lot of people do in generating random numbers is they will use the current time as a seed, right? So you're writing a C program, you want to do a simulation with random numbers, you will generate, you need some random seed to make the results different, you just use time of day. And the problem is that that is very predictable because everybody knows the time of day. And so for security purposes, that is a terrible way to generate random numbers. So the result is that this is a real problem where most operating systems have had some problem where their random numbers were not very random. One thing it can lead to is bad RSA keys where they're factorable. If you're picking random IDs to assign to people that shouldn't be guessable, like a social security number, you would like them to actually not be guessable, so this has happened. So these are real problems that have caused big problems. So what does this have to do with virtualization? So what it has to do with virtualization is this notion that you can snapshot a virtual machine, right? And a snapshot means we are saving the state and we could potentially roll back to it. So if we think about our architecture for how we generate random numbers, when we save the state of our virtual machine, we are actually saving the state of all those entropy pools. So we're rolling back the entropy pool from wherever it was as we were executing back to the entropy pool from when we first restarted the virtual machine. So if we have our randomness and we take a snapshot and we save it and we restart, then for some period after we restart, remember the entropy goes into a pool and sits there for a while before it actually gets used by dev random. This means that after you restart, the first couple times that you read from /dev random or dev urandom, you're not using any new entropy from having restarted the virtual machine. You're using whatever was in the pool when you stopped it, which means that you will tend to get the same exact values out every time you restart the virtual machine. So if you were using this to run a web server using TLS or something like that, it would generate the same secret information every time you ran it. Another thing that can go wrong is if you have an application that was running when you snapshotted, it read random information when you first started the virtual machine, and then it just did this user mode trick. When you restart it, it will always produce the same exact sequence of random numbers. Because user mode random number generators are deterministic typically. They just apply some deterministic calculation to some random number to get the next one. So for example, if you were using Apache to do this, and you started Apache and then you rolled back to a snapshot, you would generate exactly the same sequence of nonces for TLS as that you got the first time, the second time, or the third time, or the fourth time. So this means that all these assumptions about randomness that we have sort of break when you can roll time back and then replay the history. So here's sort of a picture of what happens. The application starts, it reads, it gets a key, it uses a key. We take a snapshot. On the first execution, it uses the key. We then roll back the snapshot, use it again. And so these mean that you can recover private keys from Apache as a result of doing this. Because it turns out TLS is vulnerable. If you reuse the secret information, you can actually get the sort of real secrets out from the system. Questions? So another question, yes?
How does an attacker force a reset on the virtual machine?
So an attacker can't really force a reset. What you can do as an attacker is if you can detect that a reset happened recently, So this is a difficult attack to generate, but if you know that somebody, for example, is implementing scaling up their front-end web server by restarting snapshots so they start very quickly, then you can do things, for example, like try to generate a lot of traffic that will force it to scale up and start new web servers from the snapshot. And after you've seen the first one, you can try to replay that information. So one thing to note is there are lots of vulnerabilities where sort of taking advantage of them can be difficult. And I think this is a class where it's somewhat difficult because you need to find someone using snapshots in this way, and then you need to either be lucky and see when a new one starts and happen to have been seeing when the last one started, or you need a way to force it. So it's not an easy vulnerability, but it's something that exists for the wily hacker to take advantage of. So with one of my students, Adam Everspa, we did a study of what happens in Linux to sort of see what happens when you snapshot and then you restart and read from these pools. And to sort of see, as you start reading, how long do you get the same results for? Because at some point, there'll be entropy that comes in, you'll get new results, but there's a period where you will get reused randomness. What we found is that, it wasn't entirely predictable, but we did see there was a lot of commonality. So you can see the first numbers are the same, the second numbers are the same, the third, the fourth, the fifth, the sixth, the seventh are the same. They're mostly the same. They're not entirely the same. At the end, they actually start to diverge a little bit. And so, the good news is that, 10 random numbers is not a lot of random numbers in the course of a system lifetime. But 10 random numbers you use wrongly in a web server is enough for someone to break in. So this is enough to be a real vulnerability that could be compromised. So this means what we found is that 7 out of 8 snapshots produce nearly identical outputs from the random number generator. So, again, this gets to when you assume something about your system, you really need to sort of figure out, is that assumption still true in this new environment? So people have had the same problem where they take code that is written for a server or a PC with lots of devices, they run it on an IoT device that is very lightweight, and it turns out IoT devices don't have disks, they don't really get a lot of network traffic, and they have really bad randomness. This means that if you just take your code written for a server, run it on your home thermostat, or your IoT thermometer, it might have totally not random numbers that are very easily predictable. And so again, you need to understand what you're assuming about the security of your system when you're using this. Yes?
Does this still work for those large random?
I believe it still works. So we published this work. We actually talked to Ted So, who is the maintainer of DevRandom, about how to do this, about this problem. And we actually built a new random number generator called Whirlwind. We tried to get in there. And then the student graduated before we actually got it in there. So, it takes a lot of work to get things like this fixed. So we also looked at generating RSA keys using GenRSA key from snapshots. A lot of the trials produced identical private keys. So again, if you restart a snapshot, generate a private SSH key or something like that, then your assumption of getting good randomness kind of breaks. And the reason that it happens, as I said before, is this time lapse, where the information really only moves from one pool to the next when it accumulates enough entropy. So it's really like a pool of water, where once the pool gets deep enough, it's going to overflow and spill things to the next. So when we get enough pieces of entropy in the interrupt pool, or it's been too long, we start spilling in the input pool. When we have 64 things we moved into there, we start spilling. And so this means there's some time lag before the entropy actually moves into something that's accessible. So we tried this on other operating systems. FreeBSD had the same problem for about 100 seconds after resumption. It would produce the same random numbers. So that is a pretty substantial overlap. On Windows, it produced the same output indefinitely. So when you restarted, you would get the same sequence of numbers, for hours through these 3 different things. So that is what you should learn about the importance of randomness and the problems of rolling back time and changing the assumptions on which you build your system. So we're going to move now on to sort of cloud computing environments a little bit and what are called side channel vulnerabilities. Any questions on RNGs before we do that? Yes?
Volume snapshot more secure than current rather than full.
It is more secure because it turns out, we did a study of this, when you boot your system, there's a lot of I/O activity that are really random. And so we measured when you boot from a volume on a virtual machine, how different is it every time you boot? And we found there is substantial difference in the sort of microsecond or nanosecond level timings between boots. And so it's very good. It does turn out that the first ASLR value that the system uses is generated before the devices are turned on, and so that first call to get a random number always produces the same result. So Linux has a mechanism where it can save the contents of the random pool when you shut down. So when you reload, it'll sort of reload the existing randomness pool to give you better random numbers to start with. In a snapshot, that doesn't help because you're reloading the same thing. And it doesn't help in this case where you're using random numbers before you actually have access to randomness. The good news is that Intel has introduced an instruction called RDRAND, and the Intel processors now will produce high-quality random numbers. The downside is that there were some researchers in Massachusetts who said if Intel wanted to or was convinced to, they could make this hardware produce predictable random numbers and we would never know. That you could sort of do this in a way that was totally undetectable and yet would provide whoever convinced them to do this complete access to knowing what all the random numbers are. So that sort of opens the question of how much do you trust Intel? So what people are tending to do now is to keep the same architecture of randomness and then mix in randomness from the processor also to have sort of more sources of randomness. So if anyone goes wrong, you have sort of backup sources of randomness. Okay, so now onto cloud computing. So cloud computing, you probably have heard about somewhere. So it is very popular. Amazon, Google, and Microsoft are the big three here. And what they effectively do is provide a way, one of the things they do is provide a way for customers, tenants, students to run virtual machines on their hardware. And this is pretty widely popular. You know, the number of companies that are doing it is, you know, a lot of big popular companies doing it. And really anybody with a credit card or actually without a credit card can be a tenant. So from a security perspective, you know, what does this sort of mean? It means that you potentially as an attacker, if you wanted to be, can run code on Amazon's machines or Microsoft's machines, which means there's some risk because you now totally control. When we were looking at Stack Overflows, all you could do is provide input. Here you can actually, you know, run a whole virtual machine with whatever you want in it, having complete control over that operating system. In addition to virtual machines, there's, you know, like 95 other things that come with cloud computing, a lot of storage devices, scheduling devices, security services, you know, you can, different kinds of management tools, networking tools, analytics. We are going to sort of focus on the one at the top, EC2, which is the Elastic Compute Cloud, which is really the ability to run a virtual machine in the cloud. Okay, so this is sort of a simplified model. There's a bunch of servers, thousands, tens of thousands, hundreds of thousands, that are run in data centers provided by the cloud operator. Some user creates a set of virtual machines that then get run on the cloud here. So as a user, you prepare a virtual machine image, which we talked about. It is sort of the volume, the operating system, all the data you want, as a disk file, basically a disk image, and then you give it to Amazon, and Amazon will run it. It is up to the cloud provider to pick which machines they run on. So cloud providers have some scheduling algorithm that says, given the set of machines I have, and users wanting to launch virtual machines, I will decide where to actually run those virtual machines. So this means that if you have multiple users, another feature of cloud computing is multi-tenancy. The way Amazon keeps this cheap is to say we're not going to run just one virtual machine on a physical machine. We're going to run multiple virtual machines. And this is useful because we can buy machines with lots of processors. You know, Intel just announced a 56-core processor. So they might have 56 or more cores on their system. But if you as a user running a web server that only needs 1 or 2 cores or less, you don't have to pay for the whole thing. So they'll run multiple virtual machines for different tenants, and they will share the same physical hardware. It's then the virtual machine monitor, or also called the hypervisor, that actually runs these at the same time and switches between them back and forth and shares the hardware. So the idea is, as a user of this, it looks like you have a dedicated server, just belongs to you running your code. From Amazon's perspective, they want to get lots of users on each physical machine because they can make more money by having more users. So the question, one of the things to think about is, what is the trust model here? So one thing you have to do is, as a user of cloud computing, currently you need to trust the cloud provider. You need to trust Google, Amazon, Microsoft, because you are giving them your code to run. They can look at your code and steal any secrets you put in that code. If you have, special machine learning algorithms, they can see it. If you put secret keys in your virtual machine images, they can see those secret keys. You have to trust them with your data, because if you want to, cloud companies typically charge you to, actually it's usually free to upload data, but then you have to pay to get data out. And it's also slow to upload data, so typically you'd want to upload your data, store it on drives at Amazon, Microsoft, Google, access it locally. So you're trusting these companies with all of your data. So there's a lot of trust that's going on there. You are also trusting them to secure the infrastructure from attackers. So you're kind of trusting that Amazon is not itself going to be broken into by hackers, because if that happens, the hackers can see everything that all the customers are doing. You also are trusting that Amazon employees are not going to break into your system, right? Their administrators, we hope, are not breaking in and looking at your data and looking at your secrets, because they might have complete access to everything. And so this is something else that we have to trust providers to do. So the new threat model we're interested in here is, what if there is we're going to sort of assume those things are trusted, so we have to look at what is not trusted. Well, the customers of cloud computing, that is us in the room, we are totally untrustworthy. And so this means that a malicious actor in this case is a tenant, a customer of Amazon that is running virtual machines that are trying to subvert the system somehow. So one thing they can do is they can try to get their virtual machines in good places. For example, on the same physical machine as your virtual machine, right? Because if they're in the same virtual machine, the same physical machine as you, they might find ways to sort of break virtual machine isolation and attack you. Right, so here in this example, the third virtual machine is on the same, the red one's on the same as blue. And the thing to note is virtual machines are pretty cheap. They're like 6 cents an hour. So an attacker could potentially launch hundreds or thousands of virtual machines pretty quickly in the effort to get one on the same physical machine as you. So even if it's hard to do, it might still be possible by launching lots and lots of virtual machines. So once they're running on the same physical machine, then they can look for, are there attacks where when you run in the same machine, you can attack another virtual machine somehow. This really means we need some way to break the isolation that virtual machines and hypervisors provide. And so there's a lot of research on just where those breaks are. So there's sort of a couple different ways of doing this. One is, if there's bugs in the virtual machine monitor, we can exploit those. So for example, VMware has had bugs where if you did the correct thing, you could actually get a buffer overflow in the hypervisor more or less, and then you could use that to sort of control any virtual machine you wanted. You could potentially do a denial of service attack. So if there's some shared resource, then one virtual machine can try to use it a lot and hurt the performance of the other. And the third thing is a side channel attack, where one virtual machine can potentially read data from another virtual machine. And we'll go into that in more detail. So before we move on to some examples here, any questions on this threat model? So one thing to note is this is basically the same threat model operating systems have, except instead of a VMM vulnerability, it's an OS kernel vulnerability. Instead of it being attacking a different virtual machine, we're trying to attack a different process on the same operating system. What is different here is really that the customers may come from totally different companies. With operating systems, rarely do we run code from totally different companies or people across the world on the same operating system. Yes?
Vulnerability
So this is just a bug. Suppose you have a bug in your virtual machine monitor, then that bug can be exploited. So the same way, if you have a bug in Linux, that bug can be exploited to sort of violate the isolation and security properties of Linux. The same thing is true for VMM. They can have bugs, and they have had bugs. Okay. So we're going to sort of talk, how do you do this? So some of the ingredients you need is you need to know if you're going to do an attack based on running on the same physical machine, you need to know you're on the same physical machine. And this is not actually that simple a problem to solve. Because the whole point of isolating things is so that they each think they have their own dedicated physical server, and you are trying to decide, are we actually on the same physical server? So there's a couple ways of doing this. One thing you can do is you can try doing something like a ping, and you can measure the latency to send a network packet from your virtual machine to some target virtual machine. And if the latency is very small, then it might just be going through memory on the same machine and not out to a switch in the network. If it's larger, then it's going to a switch in the network. This used to work. The problem now is that Amazon has started sort of sending all traffic between virtual machines out into the network instead of short-circuiting and sending them locally. So you can't really tell from latency anymore. Another thing which is more reliable is you can find some physical resource that the hypervisor cannot share fairly. So it turns out there is an instruction in x86 called a locked, a locked exchange instruction, which will lock the memory bus and then exchange two values in memory. It's an atomic instruction used to build sort of concurrent data structures, but it locks the memory bus. And what this means is that if one virtual machine issues this instruction, every other code running on that system cannot access memory while this instruction is executed. So if you execute this instruction a lot, it will basically slow down everybody else. And so this means, for example, if you are connecting to a web server and you issue this instruction from your virtual machine, the target web server might slow down while you're running this attack. So you can sort of measure the performance of your victim to see, are they suffering from something like this? So that is sort of a common way at this point to detect when you're co-resident. But typically you have to do something on the machine to sort of forcibly slow the other virtual machine down. Yes?
But if you slow the machine down, how can you check that whether others are slowed? Because you were slowed.
So you were slowed down too, but what you do, let me just draw a picture. So in this scenario, the attacker runs a virtual machine doing the lock exchange. It will then send GET requests to the victim web server, and it will measure what is the performance of this victim web server. And what it will look for is you want to have some pattern. So you might see something that looks like low, high, low, high. And in your attack, you're going to make your attack have some pattern also. So your attack will sort of sometimes do no exchanges, sometimes do a lot of exchanges, sometimes do no, but you look for the same pattern and latency of the web server. So if these two patterns match up, then you're on the same machine. Because it's this exchange that is hurting the performance of the web server and causing its latency to go way up. Does that answer your question? Other questions? Okay, so once we have a way of testing for co-residence, the second thing we have to do is achieve co-residence somehow. Yes?
The odds are still very less of identifying because the web service like migrate around different virtual machines and so.
Right, so you're saying that this is not what web servers look like. They look sort of like something like that.
So what I mean is, So the web service might be run on like different virtual machines across different.
Right.
So if the request, this HTTP GET request is serviced by some other.
So it's true. If you have a single web server, this technique will work. There's noise here, as I pointed out. But you're pointing out is, what if you have 10 web servers because it's a big website and they're replicated, then your requests might go to different places. So if you send enough requests, the load balancer will spread them out. But it means that the signal you get might look something more like this. That the effect is not going to be as big, or this will sort of look like this. The effect will be smaller because it's sort of an average over 10 web servers. And it's true, but it turns out this effect here is like a 100x slowdown. So even when you divide it by 10, we actually did this experiment. This is still visible even through a load balancer, that you are co-resident with at least one of the back-end web servers. But you're absolutely right. So the second thing we need to do is achieve co-residence. And the way you do this is just launch a lot of targets. So does anybody want to hazard a chance as to like how many, suppose your victim has 10 web servers and you want to achieve co-residence, how many attacker VMs do you think you need to launch to get co-residence with high probability? You know, say greater than 50% probability.
How many VMs, or do we know how, like, what the architecture is?
Well, so we know that a typical server might run, say, 16 VMs, and Amazon might have 100,000 servers. Any guesses? No. Okay. Well, clearly you know, because I'm asking you, that it's going to be a shocking number. And the answer is about 30, which is shockingly low with 10,000 machines out there, that just by launching 30 virtual machines, you can get co-residence most of the time. And this is true on Microsoft's cloud, on Google's cloud, and on Amazon's cloud. And part of the reason is that, one thing is we don't know how these companies schedule their virtual machines, but one thing they might do is they might sort of say there's a pool of machines we're scheduling on, and so all new virtual machines go onto the same pool. And so if I launch a virtual machine close in time to when you launch a virtual machine, they're likely going to be at the same pool. So that might account for it. We also tried waiting an hour, launching the victim, and then waiting an hour to launch the attacker. And it made it slightly harder. Maybe you need 40 machines instead of 30, but it still was very easy to get a virtual machine that's co-resident. And we really don't understand at all why this is the case. We don't think it should be the case when you have so many machines. But it was the case that it really was not very hard at all to get two virtual machines from different tenants running on the same physical hardware. And we call this a placement vulnerability because the scheduler is not sort of randomizing things very well. And then the final thing is to sort of launch your attack. Okay. So one of the attacks I mentioned is a denial of service attack where you're using a resource. So one of the experiments we did is we said, let's look at 5 hardware resources: the CPU, the network, the local disk, memory, the memory bus like DRAM itself, and the processor cache. And we will build code that will intentionally flood this. So for the CPU, we have CPU-bound code, doesn't access memory, it just runs out of registers. For the network, we just send packets as fast as we can. For the disk, we read disk blocks as fast as we can or write to the disk. For memory, we access random places. We access things that are guaranteed, not lots of memory that's not in the cache. And for the cache, we access data that will fit in the cache, will sort of fill the whole cache. So with a 6 megabyte cache, we access 6 megabytes of memory over and over again. And what this shows is that when we're attacking this resource from one virtual machine, and we measure performance of the same code on another virtual machine that is sharing the same core, we can see the performance degradation. So when my virtual machine used as an attacker uses a lot of network, the other virtual machine saw 150% performance degradation in their networking. What this means is that to some extent, the other machine could have used the whole network, a gigabit or something. When I run, it gets half a gigabit instead, so we're sharing it. So this means that I can, do some things to damage your performance, not too much. Similarly with disk, by doing a lot of disk traffic, I can make your performance 400% worse. and with cache, over 500% worse by accessing the cache. And the problem here is that processors really don't have a good way of, or didn't at this time, have a good way of sharing the cache. So if my code was running, I could sort of, access a lot of things and kick your code out of the cache. So this is a good way, one, to detect co-residence also, because we can see when there's interference. It's also a good way to sort of deny service to someone else or give them worse performance by intentionally using these resources. So one result of this work is that Intel has since introduced something called cache allocation technology, and it's specifically for this case, and it allows you to sort of say for your last level cache how much you want to allocate to each virtual machine. So you can sort of prevent some of this interference in your last level cache. Okay. So what I want to do now is talk about cross virtual machine side channels. This is sort of the most interesting attack that kind of scares hardware companies the most and cloud providers, because it allows you to have one virtual machine that can read data from another virtual machine, despite having separate virtual machines, totally separate memory. And it does this because it's sharing the hardware. So in this environment, we've got an attacker virtual machine and a victim virtual machine. They're using the same data cache. So these are two virtual machines that are scheduled and time sharing a single processor. This is pretty common if you've ever used what are called the small virtual machine instances. They actually only get half a physical CPU, so they time share with another virtual machine. And these are the most popular virtual machine sizes at most cloud providers. So the way you can, suppose you want to know what someone else accesses. So I'm the attacker, I want to know what you are reading out of memory. What I'm going to do is when I'm running, I'm going to completely fill the cache with my data, right? So the attacker VM is going to access lots of data, so the entire CPU cache has only read data in it. When the victim VM runs, we let the victim VM run for a little while, it will fetch some things into memory, so we can see that it evicted some of our data. When we run the attacker again, we are then going to read everything that we put into the cache, and we're going to time it. And we're going to see how long it takes to read. If we read it very quickly, we know it's still in the cache. If it's very slow to read because it has to go to memory, then we know it was evicted from the cache. And we know that the victim virtual machine read or did something to access data that went into that cache line. So we now know something about the physical addresses of the data that the victim read. So this gives us sort of very little piece of information, but it tells us something about what the victim is doing. And the key then as an attacker is to figure out how do you use this very little signal to actually find something useful. So as this part, we're going to go through this in more detail. But this is kind of the essence of what the side channel looks like. Because we are learning something about the victim virtual machine leaking through the processor cache. So here, this is just sort of some data that sort of shows how much you can see. So this is running multiple trials. This is sort of looking at what happens, and this is sort of looking at performance, and it's sort of showing when you're co-resident, what you can learn by looking at the cache. Yes?
So the previous slide you mentioned how the CPU cache goes to information.
Yeah.
But the thing is, you'll be using only a couple of bits from a physical address to index into the cache. So
Yes.
how can you use?
Well, what you have to do is find really important bits that tell you a lot of information. So you're absolutely right that there's very little information. There's just a few bits of the physical address that you get. And so that is what makes this interesting and hard, is how do you get from that very little piece to something useful. So what this data is just sort of showing that if you look at the green dots where we're not running next to an HTTP, against the red dots where we are, we can see that by looking at the cache, we can sort of see a different performance. We can see that things are faster when we're running alone and slower running with an HTTP that's doing gets. And this tells us that this is real data from Amazon, so that we can actually measure we can see measurable performance differences based on the workload we're running. So this tells us that there is a possibility of playing this kind of cache game because there are differences that we can see. I mean, sometimes they're more clear than others, but there's still a signal there. Okay, so the question was, how do we do this? So the trick is find some code that is, find something that is repeated very, very frequently that has a really clear pattern. And what people have settled on is looking at the code that is used for exponentiation in RSA. Remember, when you use your secret key, the way you're doing it is you're computing a big exponent in modular arithmetic. And the way people do exponentiation is with this sort of square with this code here. And the key says we're going to look at some bit E of our key, of our encryption key, and we're going to go through all these bits, and we are always going to square and do the reduction. If the bit is 1, we're also going to do a multiply step in reduction. So we have a code path where there's one code path where if E is 0, we execute one piece of code. If E is 1, we execute the other piece of code. So what this does is this leaves a footprint in the instruction cache. If we execute with E equals 1, we're going to execute both blocks of code, and they'll both be in the cache. If we only execute with a bit 0, we'll only see the first piece of code in the instruction cache. So this gives us a very weak signal that we can try to detect by seeing what ends up in the instruction cache. So if we look at the instruction cache when E equals 0, we're going to sort of access these two cache lines for instructions. When E equals 1, we're going to access more cache lines for instructions. And so what we want to do is sort of for each bit of the key, we want to detect these two situations. So it's tricky. It took about a year for a grad student to actually get this working, but it's doable. So the first thing we have to think about is, you know, if I run this code on 100 bits, that's going to make sure that both code paths are in the cache. So I really need to figure out how do I look at the cache right after one iteration of this loop has been run. So that has to do with scheduling. How does the virtual machine monitor schedule virtual machines onto this physical CPU? So the virtual machine monitor does a couple things. One, it decides which virtual machines actually share the same CPU, the same core. We can't control this, so here we need not just co-residence on the same physical host, we need co-residence on the same actual core of that host. It turns out that the virtual machines can also migrate over time. They might start out sharing a core, they might migrate to someplace else, so we have to worry about that. So another problem is that typically virtual machine monitors use a very coarse-grained timescale for context switching. The default in Zen was 30 milliseconds. This means that the attacker got to run for 30 milliseconds, then the victim ran for 30 milliseconds, then the attacker ran. And this is time for hundreds or thousands or millions of iterations of that loop. So it is much too coarse-grained. So we need a way to, like, what can we do to keep the victim from running for very long, right? We'd like the victim to run for like half a microsecond at a time. Okay, so what we are going to do is that what we have to do in this case is figure out what are the opportunities that an attacker has to manipulate the scheduler and get their virtual machine to run. Right? What I want to do as the attacker is to get the virtual machine that is running on the same core as the victim to run as often as possible to preempt the victim. It turns out that you can use interrupts to do this. One of the things that hardware can do is do what's called an inter-processor interrupt. This is when one processor will send a message to another processor causing it to take an interrupt and start running the operating system. Virtual machine monitors say, well, we want low latency. This means that when an interrupt comes in, we're going to immediately switch to the virtual machine that received an interrupt and start running it. So what we can do is have the attacker send a inter-processor interrupt between one virtual CPU to another virtual CPU. So here, the picture now looks like this. The attacker has two vCPUs. One of them, the one on the right, is running on the same physical CPU as the victim. So the attacker on the left will sit there in a loop that says, send an inter-processor interrupt, wait a very short period of time, do it again. The other attacker, vCPU here, is doing the prime and probe attack, where it empties out the cache and then probes the cache to see what's in there. And it is receiving these IPIs. So every time the IPI comes in, it's going to preempt the victim. The attacker, as part of handling this IPI, can now probe the cache to see what was in there, to see what the victim just did. So with this, we now have a picture where we can limit the victim to just running for 2.5 microseconds instead of running for 30 milliseconds. So about 1,000 times shorter time slice using this. Whereas the attacker gets to run for a long period of time. So one thing this really does hurt the victim, it makes the victim run quite slowly, so it's on a service attack. But it also lets us sort of inspect the cache at high frequency. So that was one of many steps. Yes?
That is running the API code that is sitting on a different.
It's a different core on the same physical machine. So we've got two cores. One of the cores is running the victim, the attacker code, sending the APIs. The other core is running the attacker VM, receiving the APIs, and the victim VM. In the same physical server, but different cores on the server. Yes. So we now have sort of a machine learning problem. So what we will do, or a signal processing problem. So what the actual outline of the work looks like is, we set up this cross virtual machine probing. We then measure what happens in the cache, lots and lots of times, and we sort of have a bunch of observations. This gives us some sort of cache patterns. We then try to classify these, because what we're trying to do is to basically do something like gene sequencing, where we have different observations of different bits of the encryption key. We want to splice them together and create the whole encryption key. So we're going to get sequences of these classified labels of different observation of bits. We're then going to do some noise reduction because there's lots of noise. We don't know when we preempted the victim. They might have been doing other things that polluted the cache. There's lots and lots of noise. And that will kind of give us the fragments of the code path they took. And finally, we reassemble this into the actual sequence of bits that they use, sort of reassembling the code path they executed. And this gives us the encryption key out. So this was actually done, in the lab on an Intel processor. And they tried this with two different schedules. It took with a work-conserving scheduler. This means that whenever there's an idle core, the VMM will schedule something on that core. So it's very aggressive at scheduling. Here it took about 6 hours, where we were doing 300,000 300 million probes of the cache, generated 300 key fragments, and then from those we could brute force the key in about 10,000 attempts, which is pretty quick. With a non-work conserving scheduler, it takes more time to do this because you may not actually run as frequently, but again, we can brute force the key. And this, let me just see what's on the next slide. So this was actually demonstrated using machines at Amazon, not just in a lab at a university, but it was shown that it actually worked on machines in the cloud. So the takeaway is, virtual machines provide great isolation, but again, we need to think about our assumptions that if they provide isolation, is it the kind of isolation we need for security? Or is it the kind of isolation we need for sort of general protection and goodness? That they have lots of nice features about transparency, they contain things nicely, but we really need to sort of think deeply about our assumptions about what the hardware can do for us. Next week, we'll talk more about the Spectre meltdown attack and sort of look at more problems that come up in hardware. So the other thing this means is that, having a secure guest and a VMM or host operating system is really important because, this is a very difficult attack, but if we can find a way to sort of a vulnerability in the VMM, we can avoid this and then just directly read memory from the victim. And so we would like to make it this difficult to some extent, which is why we need to sort of keep all the other software secure. So any questions on this cache-based side channel attacks? So this, by the way, is an example of one attack. There's numerous other ones. There's attacks on AES. This one uses the shared level 1 cache and time sharing. Other attacks use a shared last level cache when you're running on different cores, so we don't have the same scheduling problem. So people have looked at many variations of this. Yes?
Can virtual machine monitor a lot of things?
So if you know what you're looking for, then you could see abnormal traffic and see all these IPIs, and you could stop it at that point. The other thing you can do is, and we had a paper on this where we said, if you're getting that many IPs, maybe you don't deserve to run that quickly every time. And so we incorporate what we call it a minimum times context switching time. So we said when you get a context switch, when an interrupt comes in, we're not going to context switch out the victim unless the victim is run for at least a millisecond, which is long enough to pollute the cache. So that's one thing you can do. Another thing is this attack relies on a high quality source of time. You have to measure time in nanoseconds to measure a cache miss versus a cache hit. So people have looked at, can we randomize the time that the VMM gives to guest virtual machines? So they can't measure time very accurately, so they can't tell the difference. So people have tried a bunch of different things, but none of them have been that effective and deployed. They work, but they typically cause some performance loss. Yes?
That you spoke about, this is exploiting the sharing that is one cache.
Yes. The L1 cache. There are other variations of this that exploit a shared last level cache also. Yes. Okay. So I think we will pause here before we talk about other kinds of virtual machine vulnerabilities, which we will take up next time. So as I mentioned before at the beginning, a quick note, I have office hours right now until 11:45. Then I'll be going to the research symposium. Hopefully some of you will go to the research symposium as well. It's in the Varsity Hall in Union South starting at noon. And then office hours on Thursday will be at noon instead of at 1:30 because I have to attend this meeting. Okay, thank you.